Okay, thank you very much. So, hello everybody. I just apologize for my English. I'm from a French-speaking country. So I'm Aboudramane GUIRO from Naziboni University of Bogo-Dioulasso in Burkina Faso. First of all, I would like to thank the organizer of these activities, especially Dr. Augusto Folashade, who gave me the opportunity to make this presentation this morning. My presentation is about modeling dengue fever application to Burkina Faso case study. This is a joint work with some colleagues of mine from Burkina Faso and Spain. My presentation will be structured around the following point. After a brief introduction, I'll explain about the epidemiology of dengue fever. After this, I'll present a multi-serotype model of dengue fever. And after this presentation, we'll focus on one serotype model of dengue fever where we did the mathematical analysis and some simulations. So, we can say that dengue fever is a vector-borne disease. Vector-borne disease that date back to the end of 18th centuries and was discovered in Philadelphia in North America, according to Benjamin Rich here. We have to say that the first cases of dengue fever in Burkina Faso date back to 1925. After this date, Burkina Faso had no more confirmed case of dengue fever until 2012, when new cases were reported. And since that date, cases have been reported every year until today. So how about the epidemiology of dengue fever? Dengue fever is, as I said before, a vector-borne disease caused by a mosquito called Aedes aegypti. The first presenter presents a mosquito, but it distinguishes from the mosquito that causes malaria by its white spots on its body. You see that there are white spots here. This mosquito is different from the mosquito that causes malaria. It is usually bite in the evening at sunset. We have to say that the symptoms of dengue fever look like malaria symptoms also. So, how dengue fever is transmitted to human? It's a kind of cycle. It is a cycle. I mean, in fact, when an infected mosquito here bites a safe human being, this can contract the dengue fever. After this, when a safe mosquito bites this infected persons, it can also be infected and the cycles go on. We have to say that dengue fever has no cure. There are no medicine for it. We only treat the symptoms. This makes it difficult to control this disease. So, to control the control of dengue fever is essentially based on raising awareness among the populations, so human sensibilization and vector control. Let's explain now how we model this disease. There are 4 serotypes of dengue virus called dengue 1, 2, 3, and 4, which circulates around the world. A 5th serotypes has recently been discovered. We find it from this paper. It is important to know that when you recover from a serotype of dengue fever, you become immune so that serotype to this serotype, and you can only contract the other serotype. You imagine that you have 2 serotypes in your country. When you contract the first one and you recover from this first one, you can contract the second one. After this, you become immune from dengue fever in your country when you have 2 serotypes in your country. So we have schematized an environment where there are 3 serotypes as follows. If you assume that there are 3 serotypes in the countries, S represent the susceptible peoples, the safe peoples, and when you in this population you can contract the dengue virus, the first one, the second, or the third one. If you contract the second one, for example, after recovery from this, you can also contract the first one or the third one. If you contract the third one, after recovery from this, you can contract the first one. So you can see how you can contract dengue fever in a country. So we schematize this like this shape. So in Burkina Faso, we have essentially 2 serotypes which represent approximately 97% of cases. Modeling the 2 serotypes give us, so we know that we can find also a third serotype, but we neglect this due of the number of cases. Here is a diagram that model 2 serotypes, which is in Burkina Faso case. Here, we have in the center the dynamic, the different classes of the mosquitoes, and here in the right and the left, the different classes of human being. So we consider a safe human population here, susceptible. When this population meets an infected vector, an infected mosquito, it becomes a contact case, and from this, it can move to the class of infected peoples here. So the infected people, there are those who have not severe case, that people don't go to the hospital and then recover from dengue fever and they come in this case. So some of them goes to the hospital. We call them the detected peoples, and those who don't go to the hospital are called the undetected peoples here. So you heard me, I mean. Hello?
Yes,
Hello?
Guiro, we can hear you.
Okay.
Okay, thank you. Yes, we can hear you.
We can hear you.
Okay, so this population who go to the hospital, sometimes after some medicine, doctors can let them go back home. So they have not dangerous case, severe cases, but there are some of them will be kept in the hospital because they are severe case. So from these people, some will die, some died from these people, and some of them will recover and become recovered people. So these recovered people will be immune from the first case of dengue fever. So they move to susceptible peoples, a kind of susceptible people, and these peoples, if they meet the second serotype of dengue virus, they become contact cases, and from these contact cases, they can be infected and they have the same shame as in the first case. So it is the same situation in the right hand side. Safe people meet an infected mosquitoes, they became a contact case and can move to infected people, and these infected people are divided in two classes, those who are detected and those who are not detected, and we goes with the different classes. This is how we modelize the dynamics of the two serotype dengue fever in Burkina Faso. So this modelization gives this equation. So the S00 represent peoples who never been infected by dengue fever, and we have a kind of logistic dynamic here, and we aggregate the equation for the human here until here for the human. And when we disaggregate this equation, we have about 40 equations for human modelization, human classes. And we have also the dynamics equation of the mosquitoes. We have the susceptible population, the infected population with the serotype I, and we have here, if you did the right, we have two serotypes, the 1 and the 2, and we have the infected population of mosquito here. We have to say that this work is in progress. We hand with mathematical analysis, and we are now doing the simulation for two serotypes. How about the one serotype model of dengue fever? As I said in the beginning, we did the mathematical analysis of this model, and this model is in this transfer diagram. So we have the susceptible peoples and the human people here, and the mosquitoes people here. When a susceptible peoples meet an infected mosquitoes, we move to the class of contact people, those who are being bitten by a mosquito. From those populations, some of them will be infected. And from the infected people, those who have severe case goes to the hospital with detected case, and those who have not a severe case kept in home and recover from dengue fever. And the detected people, some of them can be released to go home, and the others are being kept to the hospital. So this gives these equations. We have from S to R, the dynamics of different classes of human populations, and from SV to IV, different classes of mosquitoes peoples. Yeah, we did a mathematical analysis of this, We assume that, but it is based on biological meaning of the model. We only consider solution starting at time 0, at time t0 if you want, from initial value, and the initial value of some of different classes are greater or equal to 0. So you see that the susceptible peoples are greater than 0, because if they are not disease in the population, the susceptible peoples can be all the population sometimes. And biologically reasonable also to assume that the population is finite, so, and the mosquito population also. Here you have to say that we didn't modelize the larva situation. We just modelize the mosquitoes. We have some model that we speak about the larva situation also. This give these 2 points of equilibrium. We have the first point of equilibrium we call disease-free equilibrium and the endemic equilibrium. PF is the disease-free equilibrium. In disease-free equilibrium has, his name is said, there are no disease in the population. We have just a safe human being and safe mosquitoes. And we have also the endemic equilibrium. It is the situation where we have all the situation, human, infected human, safe human, infected mosquitoes, and safe mosquitoes also. And as you can imagine, the age calculation behind this model, just for the case of one serotype, we compute also the basic reproduction number R0, which is represented by this equation here. Now, from this, we did some simulation. We have to say that we are processing data with the Ministry of Health in Burkina Faso to available the model. But in the meantime, with data taken from the literature, we have generated the following curves for the case where R0 is less than 1, and the case where R0 is bigger or equal to 1. So we have this curves simulation where R0 is less than 1. We have in the first case, the first figure here, we have in blue the infected population, the detected infected and undetected one. We focus on the detected and undetected. As you know, in our countries, when people become sick, some of them don't go to the hospital. And when they go to the hospital, when the case become severe, so we discuss sometime with medicine, with doctors, and they are interested to know about the situation when people come to the hospital. Here we have the hospitalized peoples. You see that when R0 is less than 1, the infected peoples goes towards 0. The hospitalized people also goes towards 0, and the susceptible peoples will remain higher. So it is the best situation. This means that the disease will vanish in long time. For the situation where R0 is bigger than 1, it is a situation where we have all the situation. We have safe peoples, infected peoples, safe mosquitoes, and infected mosquitoes also in the population. And we have all the time the disease in the population. This situation is not the good one. because we'll face every time to dengue fever. So here is the dynamics of mosquito population when R naught is less than 1. Yeah, here is the infected mosquitoes. You see that the mosquito goes towards 0 also, where when R naught is less than 1, so the disease will vanish. Yeah, and the situation also here where R naught is bigger than 1, where the situation where disease will be in the population every time. This is not the good one. So we did this presentation with some of our papers, former papers, with some colleagues of us, and this model is in progress. So I end my presentation and will thank everybody for your kind attention. Thank you very much.